So we're going to now talk about actor critics, and as Miguel almost revealed, actor critics are really a combination of what we've seen so far, so policy gradients and Q-learning in a sense, or more generally value functions. But to motivate them, let's first go back to the problems with reinforce. So we've seen that we can, with the policy gradient theorem, can get the gradients of this expected return by turning it into an expectation over an expression involving gradients. However, there are two problems here that Miguel also already had mentioned. First, it's data inefficient. So for each update, we need to actually collect at least one, ideally multiple episode rollouts, because the expectation is over like episodes or trajectories sampled from the policy. And that's worse than what we had in DQN, where we could update at every time step. The second problem is that the reward assignment is not very precise, at least in the basic formulation of reinforce, where we use the return of the trajectory. So essentially what we're doing is we're scaling each time step in an episode by the return of that episode, which is all right, but which doesn't really take into account that later time steps can't really be influenced by earlier rewards. Whereas what we're doing here is we take each time step and scale it by the same episode return expression. So these are two things that are not great, and two things that actor critics will address. So the first thing we've already mentioned, although really it's leading up to a first version of actor critics, and this is that we can use the reward to go as opposed to the episode return, which gives us a more localized idea of what is the value of this current time step, because we're now only considering the rewards coming after that time step and not the rewards that came before, and that didn't really matter for this current time step. And this can be shown that this is can be done with after some maths. So yeah, we've already briefly introduced that we have this reward to go. And this reward to go is really something like a Q value. It's the value of being in the state ST and taking action AT. And so one thing that we can do is, instead of estimating this expectation by collecting rollouts, we can train a function. Like in Q-learning, we train a Q function to estimate this expression. And if we do this, we basically arrive at a first version of actor critics, which I sometimes also called Q actor critics, because what they're basically doing is, instead of taking a Monte Carlo estimate, so a rollout of a trajectory to estimate the reward to go, we're just using a function approximator that we train to estimate this value. And so we can update at every time step. So to summarize here, we are now having to train two models simultaneously. We have, as before, as for policy gradient, we have our actor policy, which is the blue expression that we are training as we did for a policy gradient. And then we have our critic Q value function that we are training essentially as we did, as we trained the Q DQN and for Q learning with a form of temporal difference learning. And so in the end, a small difference that we can see here is that we're now not sampling the trajectories from the policy, but we're now sampling state action pairs. So we are now able to update at every time step. because we eliminated the need to roll out an entire episode. So yeah, that's what I just said. One advantage is its updates are based on time steps, not episode rollouts anymore. And that means we are more data efficient. We can do updates more frequently. Of course, it comes with the potential problem that we now have to train 2 models simultaneously. More to that in a later slide. All right. Maybe up to here, are there any questions? If not, then we can continue. If there's an Actor Critic 1, there's also an Actor Critic 2, and that's what's coming now. So something that is just something that you have to believe me for now, and you can find in the links that we provide on the website derivations for this. But one can show that for any state-dependent so-called baseline function, so important is a function that only depends on the state, not on the actions, we can formally show that the expectation of this expression is 0. That doesn't mean that the baseline function is 0, obviously, because it could be any function, but that it's the product of the baseline function times the gradient of the log probability, and the expectation thereof is 0. And if we look at this, so what we can do now is we can basically subtract from the expression that we had before this 0. I mean, we can always subtract 0, nothing happens, right? But that essentially means that with inside of the expectation, what we now have, we have the reward to go minus this baseline function that only depends on the state, and then times the gradient of the log probability. And the advantage here is that this is definitely mean preserving, as I just said, because we are subtracting 0, so nothing happens to the mean. But if we choose a good baseline, this might be variance reducing. So something that Miguel had mentioned before, policy gradients have a problem that their update is very high variance. This can reduce it. I'll talk a little bit more about that in 1 or 2 slides. But first, let's introduce Actor Critic 2. And because it can further be shown that for a specific choice, which is the baseline function that represents or tries to approximate the state value function, we get an optimal variance reduction. So if we can then conclude that this expression that you see at the bottom, the reward to go minus this baseline function that approximates the state value function, is another policy gradient version that has a much lower variance, but still all the other mathematical things hold. So it still does exactly the same, but it's now a lower variance estimate. And so again, to summarize, for this second version of Actor Critics, we again train 2 models, and we have again the policy that is trained with the usual policy gradient formulation, and we have a critic, this time state value function, which approximates the state value. And we can train it in the same way with temporal difference learning, basically, whether we train a state action value or just a state value. In terms of how we train it, the Bellman equations that we use to derive Q-learning apply the same for a state value function. So we basically do exactly the same. And the advantage here is that, I already said this, the gradient estimator now is lower variance. And one can say that, one can phrase it in a way to say that the perspective that we're now taking is in a way relative instead of absolute. We're not scaling our gradients in the expression above with the absolute return, the absolute reward to go, but we are scaling it with how much better was this concrete rollout as compared to what we expected. So we can see the state value as this is what we expect the state is worth. And we can see the reward to go as this is what we actually observed when starting in that state and continuing from there. If it was better than what we expected, we think this is positive. If it was worse than what we expected, then this was negative and we have to correct our policy accordingly. So that's the intuition behind it. Now, this I just assumed so far that introducing a baseline reduces variance, but it might not be super obvious. So here's a little example that hopefully makes it more obvious. So assume that we have a distribution over 3 actions in a state. Action 1 has probability of 0.2, action 2 0.5, and action 3 0.3. And we have Q values for that 6, 7, and 8 for action 1, 2, and 3. Now, if we have our estimator without baseline, this is basically what we get. We have 6 times the gradient of the probability for action 1 plus 7 times the gradient for the probability of action 2 and so on. Whereas if we are looking at the version with baseline, we assume that a baseline is 7, which is more or less what the state value would be if you have state action values of 6, 7, and 8. So basically, we are subtracting 7 from each of these 6, 7, or 8. What we get is just minus the gradient of the probability for action 1 plus the gradient of the probability for action 3. And so why is this lower variance now? If we will observe different probability gradients for each of these actions, and if they vary a bit in the reinforced expression, the result will vary a lot because each of the gradients is scaled with a big number. Whereas at the bottom version, in the baseline version, if these gradients, our estimates of these gradients vary a bit, the result will vary much less because it's scaled by a smaller number. And yeah, this is also why 1 is relative. This is relative to a center, which is around 7, whereas the reinforced version is taking the absolute values and hence generally quite big values potentially. So I hope this at least gives some idea why a baseline mathematically reduces the variance without changing the mean of the gradient estimator. All right, so this is now really a summary of now what do the practical algorithms look like that we can derive from that. First, I already mentioned this was our actor critic 1, which is also called Q actor critic, or sometimes also just referred to as D actor critic, which is where we replace our reward to go or episode return with an estimate of a Q function that we train separately. The actor critic 2, which is sometimes also called advantage actor critic, is if we take the reward to go and subtract baseline, a state value function from it. And the reason why this is called advantage, it's called advantage actor critic because this expression is referred to as the advantage of taking action A in state S, as opposed to just being in state S. Yeah, and finally, the combination of both 1 and 2, which is then an obvious step, which is also called sometimes TD actor critic, or often also goes under the same name, advantage actor critic, is to combine both. So we're using not the reward to go, but we're using an estimate involving our value function, which here is the reward of the current time step plus the discounted estimate of the next state value. This is the first part of this TD advantage. And then we're subtracting the state value of the current state. So this is really what we've seen in DQN when we have our TD update. This was the same expression, just with Q values. And yeah, if we're learning a state value function anyway, then why not make use of it to combine both versions of Actor Critic? That's why very often you see the bottom one as the real advantage Actor Critic. Okay, a few words on Actor Critic in practice. So the important point is that the reward landscape of the problem is only indirectly propagated to the actor via the critic's value estimates. So the actor never directly sees the reward or return landscape of the problem. It only sees the critic's estimates. And on the other hand, the training data for both actor and critic are determined solely by the actor's decisions. So the critic can't really directly influence the training data being collected. That's all up to what the actor decides, and hence how the episodes evolve. And this is important. So there's a dependency one on the other and the other on the first one. And both actor and critic are randomly initialized at the beginning of training, at least usually. And so really the training now is a kind of dynamic system where the critic ideally needs to evolve in tandem with the actor policy. And in particular, if we should ever end up with a very certain critic, so a very determined, a very certain actor, or which is very certain about its actions, then we're not really collecting varied experience data, because the actor is very certain that it will always do this one action also. And so the critic doesn't really get any signal to improve its value estimate. So that's a problem. If the actor becomes too certain, then the critic doesn't get good training data, not varied enough. On the other hand, at least in the case of advantage actor critic, if we have a very accurate critic, so a critic that is very good at estimating state values, then we will only get a very small training signal, because the advantage will be very small. And that's fine if the training signal is close to 0, that's fine if the task is solved. So at some point you expect your critic to become very good at it. And then you don't really need new training signal, then everything works well. However, if the critic overfits too early in training, then the actor doesn't get any training signal anymore, and hence can't improve, even though it hasn't yet learned a good policy, just because the critic learned to very well estimate what will happen. So these are problems, and that's why actor critics can be very powerful, but it's difficult to get a balance right between the actor learning fast enough but not too fast, and the critic learning fast enough but not too fast. Yeah, and for that, we also have an exercise notebook. It's not really exercises at this time, it's just basically the examples that you've already seen, in particular card poll, and something to run through, and a few plots to see how actor and critic are evolving and what the rewards are doing. And I'm not sure, I think we have a few minutes, so we haven't planned a long exercise session for that, but if you want to use, I think, the next 10 minutes or 15 minutes to just, play around a bit, look at what happens, maybe change some of the hyperparameters and see how it changes. You can do that in the next 10 to 15 minutes. And of course, if there are questions, feel free to ask them now.
This whole temporal difference learning seems to revolve around this discount factor. Does that mean that only, I mean, does it apply when you're using a finite horizon undiscounted return, or is it just for the case where you've got this infinite horizon discounted return?
You mean the one at the bottom here that we use the discount factor?
Yeah, so when we're doing this TD target thing in the bottom equation here or elsewhere in Miguel's DQN stuff or in the tabular Q learning.
Yeah, so it's very common to always include a discount factor in reinforcement learning for these theoretical motivations that were mentioned at the beginning, that if you don't have a discount factor, you don't encourage the agent to pursue anything in the short term, but because the agent has infinite amount of time, there's no punishment for doing something later and not now. So it's very common to always use it. However, I think all the equations also work out if you're just using a discount factor of 1, and so basically remove it. So in practice, that might work quite well without having a discount factor. But you will find that in almost everywhere, in at least modern reinforcement learning, there's always a discount factor just from the ground up as part of the motivation and everything. Yeah, I mean, if you're curious about it, feel free to change that. Right, you can in the notebooks use a discount factor of 1 and see whether anything happens if you compare whatever 0.9, 0.95, or even 0.99 to 1. My expectation is that it, for the actor critic, it probably won't make a massive difference between 0.99 and 1. Whereas for the tabular Q learning, it will probably make more difference because it's more directly based on just only the estimates stored in a Q table. It's not using a neural network and nothing.